Hi, my name is Franco Rotoli, and I'm a member of the SOLIDWORKS training team. This video presents a design project using SOLIDWORKS xDesign to model and build a wind-powered saw. Wind-powered machines have been pivotal throughout history, dating back to ancient Persia around 500 to 900 AD, where early windmills were used to grind grain and pump water. By the 16th century, wind power became a critical source of energy in Europe, driving sawmills to cut timber efficiently and sustainably. We carry forward that legacy by designing a modern wind-powered saw, integrating traditional concepts with contemporary CAD and 3D printing technology. In this project, we'll explore the design intent by focusing on the functional requirements of a wind-powered saw and how to achieve them. We'll discuss the integration of purchased components, such as a fan blade, saw blade, and bearings, with custom CAD-designed elements. We'll export our designs as neutral files to prepare them for 3D printing and discuss the setup and slicing process. Once all the components are fabricated, we'll assemble the saw, test its functionality, and assess its performance. Finally, we'll conduct a design review, reflecting on challenges, successes, and potential improvements. Let's get started. The goal of this project is to create a wind-powered saw that can harness wind energy to cut wooden dowels. The design must be functional, safe, and efficient, combining purchased parts with custom-made components. You'll need to consider how to transfer rotational energy from the fan blade to the cutting mechanism, ensuring the system operates smoothly and effectively. Creativity is key, so don't be afraid to think outside the box while keeping safety and feasibility in mind. Using xDesign, we'll design a sturdy base and frame to hold the purchased and custom-made components. Purchased parts, such as the fan blade, bearings, and saw blade, will form the foundation of the system, providing the core functionality. We'll create custom components to efficiently transfer rotational energy from the fan to the saw blade. Be sure to have your purchased components in hand before finalizing your design. We want to take accurate measurements of the fan, bearings, and dowels to make sure our printed parts fit properly. For my design, I took apart an old space heater for the fan blade. The shaft diameter was smaller than the 5/16 dowel I was using, so I drew up and 3D printed an adapter. Many manufacturers offer CAD model downloads from their websites. Be sure to take advantage of this when doing your initial research. It'll save time measuring and modeling. The base will be about 200 by 200 millimeters. I'll remove some material to save on filament and add some fillets for aesthetics. Take extra care in designing the dovetails. Every 3D printer has different tolerances, and even the print orientation can play a role as to how they fit together. With my setup, a clearance of 0.5 millimeter on each side gave me a good tight fit. The walls will be about 125 millimeters tall, with a hole about 0.1 millimeters bigger than the bearing. Again, every 3D printer will print differently, so experiment with sizes. The dowel holder has a 60-degree opening to cradle the dowel to be cut, and has a slit to accommodate the saw blade. Experiment with different interfaces and clearances. Print small sample files first until you are comfortable with the interface dimensions. Take care to design each component to integrate with the purchased parts. Putting all your parts together in CAD will allow you to simulate how it all works together, and will draw attention to any alignment issues before any final parts are printed. Once all the custom components are modeled, we'll export them as STL files for slicing in the 3D printer software. These files will ensure precise fabrication, aligning with tolerances needed for assembly and operation. The slicing software will allow us to adjust settings like layer height and infill density to balance strength and material efficiency. Watching our parts come to life on the 3D printer will give us insight into modern manufacturing processes and how designs translate into physical products. After printing, we'll clean and prepare the parts, then assemble them with the purchased components. We'll pay attention to fits and tolerances, especially between printed components. During testing, we'll evaluate how well the wind energy transfers to the saw blade and how effectively it cuts wooden dowels. Adjustments may be necessary to refine performance and address any issues. In the final design review, teams will share completed projects, discuss challenges, solutions, and lessons learned. Here, we see that the cam does not fit snugly into the dowel and causes the saw to stop cutting. I made the hole for the dowel a bit smaller and made the cam bigger overall. I also made a hole in the cam and used a small screw to reduce friction on the saw blade. Take these as learning opportunities to design different interfaces between components. A design review is an opportunity to compare designs, showcase creativity, and explore how different approaches influence the functionality of each machine. The wind-powered saw project is a hands-on exploration of energy transfer, engineering design, and problem solving. Thanks for watching. If you found this video helpful, click the link in the description below to access more great content.